Alright, you can probably hear some rumbling outside because of construction, but whatever, this won't be long because this is the first exercise in Serre's book on linear representations, and it is easy as you would hope. So, for all S and G, chi plus chi prime squared of, and then I'm going to write this as phi, then alpha. You know what? I'm going to not do that. I'm going to write it as beta, and beta is going to take the place of sigma and alpha, and I'll explain when it does what after the computation. Actually, no, let's do that before. If we let beta equals sigma when this plus minus will correspond to plus, and beta equals sigma when this plus minus is actually minus, we have chi plus chi prime squared beta of s equals 1/2 of, so here we have chi s plus chi prime s squared plus or minus, and of course you can go back and review what these all mean, what they all mean in the text. It's all in there. So it's going to be plus or minus chi of s squared plus or minus chi prime of s squared. Of course, the plus minuses correspond to whether beta is sigma or alpha. Okay, so that's that. Now this is 1/2 chi of s squared. We can bring, or yeah, we do that. We basically FOIL this. Because we can do that. Because remember, chi is the trace of a matrix in V, and the matrix takes on elements in a field, and so all these chi's are giving us elements of the field. Okay, so if rho goes from G to GLV, and V of vector space over F, where F is a field, then chi of an element will give us the trace of a matrix in V, which is an element of the field capital F. Okay, so we can FOIL this and it works out fine. Yeah, I guess that it's useful to include that, especially with this being the first exercise of the chapter. There's a lot of stuff going on in these definitions, and you have to keep everything in mind. But once you do it, most of the rest of the stuff is pretty straightforward. So this is chi prime s squared, and then this is plus or minus chi s squared plus or minus chi prime s squared. Okay. So now this, so we have the 1/2, and then we can put the chi s squared plus or minus chi s squared. Can put this together. Taking the first one and the one later on. This is all going to be just a bunch of moving stuff around. Then we have put the chi prime s here, and then we put the chi prime s squared. We group these together, and then we also have the 1/2, and then what are we forgetting about? We're forgetting about that 2 chi s chi prime s term. This all. And now what is this? Well, this first term is just chi squared beta of s. The second term is chi prime beta s squared. And then, so this is really chi prime squared, but I didn't want to make it look like chi to the 12th. Whatever, you should get what I'm trying to say. And then the other thing, the 1/2 and the 2 cancel, and we just get chi s plus chi prime s as desired, because these are precisely the formulas that we are trying to prove here. If you replace beta with sigma, and why did I put sigma twice? This should be alpha. So this is the this is the first formula when we let beta equal sigma and plus minus b plus, and it's the second formula when it is the second formula when we set beta equal to alpha and plus minus equal to minus. And so there we go. Despite some stuttering at the end there, we have completed this proof.